All right, today we are diving deep into Meta AI's Segment Anything project. And let me tell you, this is a big one. We're talking about a fundamental shift in how we think about computer vision. They're not just introducing a new model, they're introducing a whole new task, a massive new data set, and a completely new way of building these huge foundation models. Honestly, if you're in vision research, you have to know about this. It's that important. The entire project really just boils down to one incredibly ambitious question. What if you could build a single model that could segment anything? And I mean anything. Not just, cats and cars like we're used to. We're talking about any possible object in any image, anywhere. This is really the hunt for a true foundation model for vision, and that's the big idea we're going to unpack right now. So this is what we're talking about in practice, right? On the left, you've got your input image. And on the right, that's the goal, a perfect pixel-precise mask outlining the object. The ability to just generate a mask like this for any object just by clicking on it or prompting the model, that has been a huge challenge in segmentation for a long, long time. So let's get into how the team at Meta actually pulled this off. Okay, so here's how we're going to break this down. First, we'll talk about this whole idea of a foundation model for vision. Then we'll get into what they call the segment anything trinity. It's the core of their solution. After that, we'll look at the model itself, SAM. Then, the really wild part, the billion mask data engine. And finally, we'll wrap up with its zero-shot power and what this all means for the field. All right, first up, this whole quest for a GPT-3 for images. For years now, the NLP world has had these huge general-purpose models trained on basically the entire internet. But in computer vision, we've had really powerful models, for sure, but they've always been pretty specialized. The field has just been missing that one truly general, promptable model for a fundamental task like segmentation. So why? Why has this been so much harder for vision? Well, the answer is actually pretty simple. It all comes down to data. I mean, think about it. The internet is just packed with text data for NLP models to learn from, but it's not packed with billions of high-quality, pixel-perfect segmentation masks. And that basic lack of data has been the number one thing holding the entire field back. Okay, and that big data problem, that leads us straight to the core insight of this whole project. This is where things get really clever. The researchers realized that the task, the model, and the data, they weren't three separate problems to solve. No, they were all part of one single interconnected system that had to be tackled all at once. And you can see it right here in their own words. They talk about these three interconnected components: a promptable task, a model to do the task, that's SAM, and a data engine. The key thing here is that they all work together in this amazing loop. The model helps create the data, which then makes the model better, which then creates even more data. It's a self-feeding cycle. So let's just lay out this trinity one more time, nice and simple. First, you've got the task, promptable segmentation. Basically, you give the model a prompt, like a point or a box, and boom, it gives you back a valid mask. Second, you have the model, which they call SAM, and it's built to do this task super fast, in real time. And third, the dataset, the massive SA1B, which was created using this wild data engine, where the model literally helps create its own training data. It really is a brilliant flywheel. Okay, so let's zoom in on the model itself, SAM. The way they designed its architecture is super smart. It's purpose-built for two main things. One, being incredibly fast for real-time performance, and two, handling ambiguity. And both of those are absolutely critical if you want to build a system that people can interact with using prompts. So here's the secret sauce for its speed. The whole architecture is designed for maximum efficiency. You have this big, heavyweight vision transformer that does the hard work of processing the image. But, and this is the key, it only does it once. It creates this embedding. After that, a super lightweight decoder can take any prompt you give it and spit out a mask in about 50 milliseconds. It's this separation of the heavy lifting from the quick response that makes the whole thing feel instantaneous and interactive. And here's a perfect example of what I mean by handling ambiguity. Look at this logo. If you just click a single point right in the middle, what do you actually want? The letter Z, the little circle around it, the whole word Zurich? A simple model might just guess, but SAM is designed to be ambiguity aware. So instead of guessing, it just outputs multiple valid and plausible masks. It lets the user or some other system make the final call. It's a much smarter way to handle it. Okay, now we get to what I think is the real methodological breakthrough of this whole paper, the data engine. This is how they cracked that massive data scarcity problem we talked about. This is how they created the single largest segmentation dataset ever. So how'd they do it? Well, it happens in 3 stages, kind of like leveling up. In stage 1, it was assisted manual. Human annotators used an early version of SAM like a smart paintbrush to label masks. Then, in stage 2, it became semi-automatic. The model got better so it could automatically find and label the easy stuff, letting the humans focus on the tricky parts. And then, the final stage, fully automatic. The model was so powerful at this point, they just fed it a grid of points on an image and it would generate almost 100 masks all by itself. The model literally built its own data set. It's incredible. So what was the end result of this incredible data engine? 1.1 billion high-quality segmentation masks. Just let that number sink in for a second. It is an absolutely mind-boggling amount of data. So let's just take a quick tour of what this SA1B dataset actually looks like. I mean, check out the incredible detail on these lovelocks. Every single one is individually and precisely segmented. Or take a super complex scene like this basketball game. It's not just the players. Look, it's every person in the crowd, the backboard, the hoop, absolutely everything is treated as a segmentable object. And this level of detail holds up even for really fine-grained stuff. You look at this plate of food, and you can see even the smallest individual ingredients have their own masks. And one more, just to really drive home the scale. A library. You've got masks for lamps, tables, windows, and literally thousands upon thousands of individual books on the shelves. The density and quality across this dataset is just, well, it's unprecedented. Okay, so we have the model, we have the massive dataset. Now for the big payoff. What's its zero-shot performance actually like? In other words, how well does this thing work out of the box on tasks and images it's never seen before? And this table really just puts the scale of what they built into perspective. I mean, look at this. At 1.1 billion masks, SA1B is more than 400 times larger than the next biggest dataset. We're not just talking about an incremental improvement here. This is a completely different league. And it's that insane scale that unlocks its powerful ability to generalize. And this part is really important. The authors didn't just build this thing and throw it out there. They also did a deep, responsible AI analysis. And what they found is super promising. The dataset has way better geographic diversity than older datasets. And even better, the model itself performs really consistently across different groups of people. And you can see the data right here. When you look at how well the model segments people, the performance across different perceived genders and skin tones is basically identical. The numbers are so close their error bars overlap, which is just strong statistical evidence that it's performing equitably. For a foundation model this big, that is a seriously impressive and critical result. And all of this brings us to the most exciting part, really. Meta has released everything openly, the model, SAM, and the entire billion mask dataset. So the question for us, for the entire research community, has totally changed. It's not about if we can build a foundational model for segmentation anymore. The question now is, what are we going to build with it? What new foundational research is this going to unlock? The possibilities are wide open.